Okay, yeah. Welcome everyone. Happy reading week. Hope you are getting some rest, well-deserved rest. And today we are. So actually, let me start off with just introducing the study group in case you're a bit new to this. So our study group actually started in September of last year. So we at that time we were going through a Coursera course together. It was the Introduction to Deep Learning course. So we actually went through all the modules. So now we're just taking some time also for just to allow more others to join in as well. We're having these review or like crash course style workshops. So in each workshop, we'll look at a common problem or a common problem or topic that's in machine learning, and then try to learn some theory behind it as well. And those theory will be presented alongside with the problem. So so that's the kind of workshop we're doing now till I'd say April. Yeah, so there will be more workshops to come. But today, the focus will be on digits classification. I think this is a pretty common classification problem. So if you already taken an intro to machine learning course, you've probably done this sort of lab before. But today we'll be going over this problem. We'll look at how to tackle the problem and also explain a bit of the theory behind it. So it'll be a nice introduction and crash course on this topic. Yeah. Okay. Here I just listed the parts that we're gonna go through today. Yeah, and feel free to let me know if you have any questions, and we can discuss more at the end as well. So we'll start off with the problem. So as always, I think in whichever field, you always start off with the problem, right? What's the problem we're trying to solve? And today we're trying to do digits classification. And then when we talk about machine learning, of course, we're going to talk about data. So where are we going to find the data, and how are we going to use this data for training? And of course, a pretty important part is the model. So what neural network architecture to use in this case. And once we have the model, how do we want to train it to learn the data, right? And finally, as always, it's good to evaluate your performance, whether the model is doing good or not, right? Yeah. So these are the steps and the concepts we're going to cover. Oh, hold on, let me just find someone. And then at the end, we'll look at a more applied lab example as well. Okay, so the problem we have here is we'd like to recognize handwritten digits as shown here. So this is, like I mentioned, a pretty common classification problem. So you can, in this image that I put here, so you have maybe 7, 8, 2, and then you want to recognize this, oh, this is 7, or oh, this is 8. So the model should be able to recognize this. Yeah, pretty cool problem. And the data that we're going to use is the MLP data sets. So it has these images of these digits. And if you like to get to know some of the specifics of it, so these images, they're 28 by 28 pixels. There's the training sets, and there's also the testing set. So the training set is what you use to train the model, and the testing set is what you're going to use to test it. So for the training, you have 60,000 samples, so 60,000 images, and then for testing, you have 10,000. It's quite large. There's I found this picture here. So this is a partial group of it. So you can see you have the 0, the 1, the 2, the 3, all the digits here, and they're all slightly different since everybody's handwriting is different. So, and because of how this data is formed, you can sort of deduce that if we're talking in terms of data, then this is the dimensionality of it. So for the training set, it would be 60,000 for 60,000 pictures, and since it's 28 by 28 pixel, the other dimensions are 28 by 28. So this is the sort of like the structure of it, I would say. And accordingly, for testing, you also have this. So that's the input images. Of course, there's also the targets, right? When we train, we have to know the answer key of some sort. So this is like the answer. So as an example here, if you have 0, then the corresponding label or target should be 0 as well. So for this one, it's an array of size 60,000 or 10,000 if you're looking at the training set or testing set. So it would have a target for each image. That's why the size is like this. And then of course the target or the label would be 0 to 9. So they would represent what each image is showing. Yeah. So that's the data that we'll be using. But once we get the data, we can't just, well, typically it's hard to use the data directly, right? I find from my experience, I find that data processing is actually a big part of this whole process as well. So we have to do some data processing. In this problem here, it's more simpler. So there's not too many data processing to do. There's just 2 parts of it. So this is just to allow for easier training, right? So first, we want to simplify the data a bit. So we flatten the input, or we can say that it's reducing the dimensionality of it. So we mentioned in the last slide, the data is represented in this format. So 60,000 by 28 by 28. But if we multiply the 28 by 28 together, so just flattening it and reducing the dimensions, we get this new form of data. And that's just easier if you have less dimensions. And it's always good to have simpler data to train. And the other part is, since we're doing a classification problem, we want to convert the target. So what we said, 0 to 9, we want to convert it into one-hot encoding since it's categorical data. And what one-hot encoding is, basically, if you look at this diagram here, in this example, it's different colors. And how I see it is just you put the 1 in a different slot. So red would be 100, yellow would be in 010, and green would be 001. And so that was for colors. For our problem, we're dealing with 0 to 9. So it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it would be like this instead. So for 5, it would be 1 over here. And this would be the one-hot encoding for our 5. The reason why we do this is because if you just directly give it 0, 1, 2, and 3, you can tell like 1, 2, and 3, it has some sort of order in it, in the set, but we don't want that. So I've put here, so this 0, 1, 2, and 3, they don't have dependencies. So once we put it in this form, it's non-ordinal. So that's why we want it in the one-hot encoding format. Yeah. So that's the data processing part. Now we're going to look at the model itself. So it all started with neurons. So yeah, it's just a biological reference of how neural networks came to be. So scientists first started off by looking at, so they first started to understand how neurons work and how the brain electrical signals are transmitted. And you find that you can actually apply it in machine learning as well. So I found this image here. It's a nice comparison. For neurons, you have these structures and it sends signals. But for machines, we can also have similar math here as well, and to use this to transmit information. So you have the input, you have some bias, and you perform a computation to get this. So that's what the neuron does. That brings us to the next slide. So a neuron, it will compute the output based on the inputs and the weights. So the input would be the input data you're feeding it, and the weight will be what will be optimized. So you'll be tuning the weight as you train so that you would have better predictions and results. And another component of this is the activation function. So similar to a neuron, how a neuron fires, you also have an activation function to control when the neuron fires. So this is a structure of a multi-layered perceptron, or MLP. You have the input here, so for us it'll be the image data, and then you have the weights. You have some sort of computation and activation function too after you get the output, and here is the output layer. So this is its structure. And if we bring it out a bit more, MLP has different layers in it. So there's the input layer. The input layer is basically the layer that gets the input, hence the name. We also have hidden layers that perform the important computations in order to make the predictions. And then the output layer. So that's it. It would display the output in the corresponding format that you like. So this is the MLP structure. Oh, is my audio? Wait, okay, thanks for letting me know. Thanks for letting me know. Actually, yeah, let me grab my headphones. Sorry, just a moment. Okay, is it good now? Is it better now?
Yep, it's much better now.
Okay, that's good. Thank you. Okay. Yeah, feel free to let me know in the chat if there's any issues with the audio or the screen. Yeah, thank you. Okay, where were we? Yeah, so that was the model, right? We have the model. Let me just come back here. We know what kind of model we want to train. And so now we move on to the training. So how it trains is, just to give you an overview, so there's a loss function that you use to calculate the error between the prediction and your label. And your label would be the answer key. So 0, whether it's 0 or 2, whether it's 0 or 1, or so it would be between 0 and 9. So this would allow you to get the error that your current prediction has. And then, so after you get the loss function, you use back propagation to send this loss through the network. So like backwards like this. and adjust the weight accordingly. So like we mentioned in a few slides back, the weight is what you try to optimize in order to get better predictions. And then you use gradient descent to optimize the weight based on this error. So those are the parts of it. And to show you in a diagram here, so you have a forward pass where you calculate the error. And then after you get the error, you send the error back to through the layers so that you can optimize the weight accordingly. And then, of course, by optimizing the weight, you would get better predictions each time. So that would be how you train it. Okay, so we've went through most of the steps. I'm just gonna, so the lab that I'm using the lab is using Tensorflow. So I'm just also gonna give a quick Tensorflow introduction as well, just so you can connect the dots between the steps and the code. So Tensorflow, essentially, it's used to describe computational graphs. And an example of a computational graph is here as well. So in this picture here, basically a graph, it has a network of nodes, as you can see here, and each node has operations with inputs and outputs. So you can see here it has inputs and outputs. And tensors, so tensor is in the name, tensors are essentially multi-dimensional arrays. So if you remember back in the first few slides, essentially these input data and these targets were working with higher dimensions. So these would all be tensors that we're gonna be looking at. So this is the parts of it. And in TensorFlow, we have these, yeah, I see a raised hand. Do you have a question? Yeah, feel free to unmute.
When you say the operations, are they just the regular mathematical ones, like addition, subtraction, things like that? In the nodes? Can you go back one slide?
Yep.
Yeah. Yeah, so like the plus operation, the multiplication, so these operations are just the regular mathematical ones?
Yeah,
Okay.
They're just mathematical operations. Yeah.
Okay.
Yep. Okay. And yeah, so that's on the TensorFlow graph side. And in TensorFlow, there are also different input types. So I think we're a bit used to, so from other languages, we're more used to variables and constants. So variables, they must be initialized and they can be modified. And for constants, they cannot be modified. In TensorFlow, there's also a placeholder, and in these placeholders, you must be feeding a tensor into it, hence the name placeholder. So that's another input type, and you use these different types essentially to perform operations, like we mentioned before, and these operations would transform input output. Yeah, so that's the different components of it. Okay, so yeah, that was a quick intro of TensorFlow, and how we're going to apply this in our model is I've put some more details here. So in a previous slide, we talked about placeholders. So let me also admit someone in the waiting room. So they must be fed a tensor. So the tensors that we're feeding in our example would be the features, which is just a fancy way of saying our input data. So we would be looking at the input features. And also the target, so the label. So this is the data that we have, and they're in the form of a tensor, and we will be feeding them into placeholders when we train. And of course, in this problem, we're going to be dealing with probability. So when you predict something, when you make a prediction, when you
when the model looks at this image, it's gonna try to get the probability of it being a 0, or the probability of it being a 1 or 2 or 3. And this probability is going to be calculated using this softmax function that we're going to use. So it's going to be a predefined function, I believe. Or yeah, there's going to be some math involved that calculates this probability, and this kind is used particularly in classification problems. So that's why we're using it here. And we talked about the loss / the error. So of course we want to know when we make a prediction, how far is it from the actual answer, right? So we're going to be using this cross entropy loss. Yeah, so there's gonna be a lot of math behind this. So if you're interested, I have a slide down with all the resources. So if you're interested in the math, feel free to check out those links. But yeah, I'm just gonna list what it's called here, and we're gonna use them in our problem. Okay, next. So the variable that we're gonna train here is the weight. Like we mentioned before several times, we wanna optimize the weight so that we can get better results. And speaking of optimization, we have optimizers. So TensorFlow has these predefined functions, gradient descent or atom optimizer. So you can use them to optimize the weight to get better prediction results. Yeah, so that's sort of how we're going to construct the model using TensorFlow.